On page 45 we have an overview of the simplest class of organic compounds called hydrocarbons. And as the name implies, hydrocarbons contain only hydrogen and carbon. Now, hydrocarbons can be divided into several classes. Those that are unsaturated and those that are saturated. Start with saturated hydrocarbons. They're called alkanes, also called paraffins. Now, the alkanes contain only single bonds, which are called sigma bonds. They are saturated with hydrogen, which means you can't chemically add any more because there's all single bonds. A simple example is ethane, C2H6. Now, the alkanes can be divided into those that are cyclic, called cycloalkanes, and those that are acyclic, that have no rings. So, an acyclic alkane will have the general formula C to the N H2N plus 2. And you can check these formulas as we look at structures. Acyclic alkanes can be divided into those that are branched and those that are straight chain or unbranched. So an unbranched alkane is just a string of carbons connected together by single bonds with no carbon groups on the side. And these are referred to as N-alkanes. N stands for normal. So this is N-butane. It's unbranched. Branched alkanes have one or more carbon groups on the side of a chain. This example is isobutane. Notice the same formula, whether it's straight chain or branched. We'll teach you how to name these in just a very short time. The cycloalkanes will have the formula C to the N H2N for one ring. So by closing a ring, there's need for two less hydrogens. So notice two less hydrogens with a single ring. The example here is cyclopentane, C5H10. The unsaturated hydrocarbons, they contain some pi bonds. They are not saturated with hydrogen, and there's three classes of these. We have alkenes, also called olefins, an example of which is ethylene. There are alkynes, such as acetylene, and there are arenes, also called aromatics, such as benzene. Now, the alkenes contain one or more double bonds. So an alkene with one double bond will have the formula C to the N H2N. It has two less hydrogens than a saturated alkane because having a carbon-to-carbon double bond requires two less hydrogens to complete the valency of the carbons. Ethylene is the simplest example. Now, this is an example of an acyclic alkene. We can also have cyclic alkenes, which we have a ring and one or more pi bonds. If we have a single ring and a single pi bond, the general formula would be C to the N H2N minus 2. That's 4 hydrogens less than a saturated acyclic alkane, 2 hydrogens less required for closing the ring, 2 hydrogens less for the pi bond. This example is cyclopentene. The ending ene implies an alkene. Alkynes have one or more carbon-to-carbon triple bonds, and so an acyclic alkyne with one triple bond would have the general formula C to the N H2N minus 2. Again, each pi bond requires 2 less hydrogens compared to the saturated acyclic alkane. This is the simplest example, is acetylene. The aromatics have a cyclic, completely conjugated pi system. Now, in this course, we're only going to consider benzene and derivatives of benzene. It has 6 carbons in a ring. Notice the fully conjugated nature. It's pi, sigma, pi, sigma, pi, sigma. In truth, aromatics include more than just 6-membered rings, but that's a subject of a later organic course. So the non-aromatic compounds, the alkanes, alkenes, and alkynes, are collectively called aliphatic, and the word from Greek literally means fatty. On page 46, we'll begin to learn to name and write the structures of the alkanes, and this is titled Homologous Series of Acyclic Alkanes. Homologous simply means of like kind. Recall that acyclic alkanes, that is open chain alkanes, have the general formula C to the N H2N plus 2. Now I know I've covered some of this with you already in the first lesson, but we will very quickly go beyond that. The simplest alkane is methane, and the condensed formula for that is CH4, and we can't draw a skeletal structure when there's only one carbon. Ethane, C2H6, we've written as CH3 for a condensed formula, and we can draw a skeletal structure for that. We draw it on an angle usually. Again, a line implies a covalent bond with a carbon at each end of the line or at each intersection point with as many hydrogens as necessary to give carbon 4 bonds. The angle is reminiscent of the bond angles in the alkanes, which are typically 110 degrees in a tetrahedral carbon. Now propane, C3H8, has this condensed formula, and we'd write it like this. That's 2 carbons and then 3. So the first line that you draw is 2 carbons, and every line after that is 1 more. We get to butane, C4H10. There are actually 2 different isomers of butane, as you see. We have straight chain or unbranched butane, which is referred to as N-butane, meaning normal, straight chain, or unbranched. There's the condensed formula. Here's the skeletal structure, 2, 3, and 4. But butane can also exist in this structure. We'd have 3 carbons in a chain and 1 methyl group as a branch. Same formula, C4H10. These are isomers. They're called structural isomers. So we'd write that as CH3, CH, and we'll put the methyl group in brackets, and finally CH3. So isobutane and N-butane are isomers. And what are isomers? Well, they're compounds with the same molecular formula, C4H10 in this case, but different structures. And these 2 compounds are called structural isomers, also called constitutional isomers. That's a bit less commonly used, but it is used. And they have similar, but not exactly the same physical properties. They would have similar melting and boiling points and densities and solubility, but they're not exactly the same. And we'll discuss a little bit about that later. Now, there is in place both the common name system and the Iupac name system. The common name is limited to a few molecules, and yes, you have to learn it because it is more commonly used than the Iupac system for simple molecules. Once you are familiar with it, by choice, you will not use the Iupac system. Few people do because it's cumbersome. The common system is very easy to use when there is a name for it, but again, it's very limited. So isobutane, here's the first thing you need to memorize. Iso in a name means there's a methyl group situated on a carbon next to either end of a chain. So here's our methyl group, and it's on a carbon that is next to one of the ends of the chain. And that's the meaning of iso. There is in place the Iupac system, and we'll get to this very shortly. Every organic compound has a unique Iupac name. In the Iupac system, this is called 2-methylpropane. So we name the longest carbon chain as the parent name, which is propane, and we list any branches. There's a methyl branch on the second carbon. So it's 2-methylpropane is the Iupac name, aka isobutane. Let's look at the pentanes. There are actually 3 isomers of pentane. We have N-pentane. There'd be 5 carbons in a row. We can draw the skeletal structure right here. There's 2, 3, 4, and 5. There is also an isomer called isopentane. structure is shown here, but let's draw it. There's 2, 3, 4 carbons in a row with a methyl group second to the end carbon in a chain. We would draw the condensed formula as CH3, CH methyl, put the methyl in brackets, CH2, CH3. 5 carbons in total, C5H12. Now the name for this in a Iupac would be 2-methylbutane. The longest carbon chain is 4, so it's called a butane, and there's a methyl group on the second carbon from the end. So we number this carbon 1, 2, 3, 4, and we number the chain to give the first substituent or first substituted group the lowest possible locant number. The locant number is the location number. So this would not be named as 3-methylbutane. Rather, you would not number it from right to left, but you number it from left to right. You see, each compound can only have one unique Iupac name. You can't have two names for the same compound. There's a third possible isomer that you see drawn here. Let's draw the skeletal structure. 3 carbons in the main chain, and then 2 methyl groups on a carbon that is second to the end of the chain. And there's a name for that in the common system. That is called neopentane. So neo means there are 2 methyl groups on a carbon next to the end of a chain. Let's draw the condensed formula for that. It would be CH3, C-dimethyl, put the methyl groups in brackets, and then CH3. The Iupac name for this, well, let's number the chain. Doesn't matter whether we go left to right or right to left. There are 2 methyl groups on the second carbon, so it's named as 2,2-dimethylpropane. Now, students often ask, do I have to write 2 and 2 twice, or do I have to say di? Yes, you can't leave any part of that out. Give the complete name. Continuing with alkane nomenclature on page 47. We're looking at 6 carbon alkanes. Notice there are 5 different isomers, 5 different structural isomers of hexane. I filled most of this page in for sake of time, but we can still draw skeletal structures. So N-hexane, 2, 3, 4, 5, 6. So that's called straight chain unbranched N-hexane. N stands for straight chain or unbranched. As expected, there's isohexane. Isohexane has a methyl group on a carbon second from the end of a chain. 2, 3, 4, 5 in the main chain, and a methyl group on the second carbon. The Iupac name for this, let's number the main chain. 1, 2, 3, 4, 5. I number it from the end that gives the methyl group the lowest locant number. Therefore, that is 2-methylpentane. Note how it's written. 2-methylpentane. You add up 5 carbons from the pentane plus 1 from the methyl group gives you 6, and that equates to some type of hexane. As expected, there's a neohexane. Neohexane should have 2 methyl groups on a carbon second to the end of the chain. So there's 2, 3, and 4 carbons in the main chain, 2 methyl groups second to the end. Let's number the chain. 1, 2, 3, and 4. Longest carbon chain is 4. It's a butane. It would be 2,2-dimethylbutane. Notice the naming. 2,2-dimethylbutane. Something that students often miss is remember that you want to separate numbers from other numbers with commas. You couldn't write 22 because we'd be looking for the 22nd carbon for the group. 2, 2. But remember to separate numbers from letters with hyphens. It's a small error, but there will be a small deduction if you forget to do that. So the first 3 isomers we knew how to name in the common system. There's 2 more. Over here we have a methyl group on the third carbon in the chain. So that's 5 in the main chain, 2, 3, 4, 5, with a methyl group on the third carbon. Kind of cramped here, sorry. There's carbon 1, 2, 3, 4, 5. And so the name for that in Iupac is 3-methyl pentane, total of 6 carbons. Here it is, 3-methyl pentane. There is a 5th possible isomer, as you see here, but let's draw it. 4 carbons in the main chain. That's 2, 3, 4. Longest carbon chain is 4, with 2 methyl groups on the second and third carbon. There's 1, 2, 3, and 4. That would be named 2,3-dimethyl butane. Here's the name, 2,3-dimethyl butane. Now you might be wondering, well, we had common names for the first 3, but not for this last 2. How come? The common system is not systematic. It's not universal. There are only common names for a relatively small number of compounds. Furthermore, it's not always systematic. For example, you may have heard of isooctane. Isooctane is a fuel that burns with minimal knocking. It burns well in an internal combustion engine, and it is assigned an octane number of 100. Now, it doesn't mean it's the best fuel. There are better fuels than isooctane. Ethanol is better in that regard. They burn better. But isooctane is chosen as a standard. It's assigned an octane number of 100, and other fuels are compared to it. You probably go to the gas station to fill up with 86 octane or 87 or 89 or 92 compared to isooctane. The name isooctane doesn't really fit our system, does it? Look at the structure. You can see on the right side there is an iso configuration. We have a methyl group second to the end. That is true. But on the left side we have a dimethyl arrangement on the second carbon from the end. So why isn't this called isoneooctane? Why is it isooctane? So you see the inconsistency of the common system. The common system is systematic up to 6 carbons. Beyond 6, it's pretty loose, doesn't always work. So up to 6, you need to learn them. I've been mentioning Iupac. By the way, what is Iupac? Iupac stands for the International Union of Pure and Applied Chemists. It is an international body of renowned chemists who meet annually in Geneva, Switzerland, to decide upon conventions in chemistry such as nomenclature, for example. Now take a look at this chart of the number of isomers of alkanes. You may be wondering, I wonder how many there are. So when we had propane, there was only one possible way to draw propane, one isomer. But when we encountered butane, we found that there were actually 2 different structural isomers of butane. When we got to 5 carbons, we found there were 3 ways that could be drawn. With 6 carbons, we've just seen that's 5 different structural isomers. What happens with 7 carbons? Well, there are actually 9 different isomers. With C8, H18, that's octane, there are actually 18 different isomers of octane. So all octanes are not the same. C9, H20, that would be nonane, there are in fact 35 different structural isomers. This almost looks like it's doubling each time you add a carbon, doesn't it? So for C10, for decane, there are in fact 75, almost exactly double the number of structural isomers from 1 carbon less. When you get to C15, there are in fact 4,347 different isomers of carbon 15. We haven't scratched the surface. And when you get to 30 carbons, you're not going to believe this, there are 4,111,846,763 different structural isomers of a 30 carbon alkane. Now you wonder, how could they know that? This can be calculated using combinations and permutations and statistics. Have we discovered that many? No, we're far away. Remember, there was only approximately 30 million plus known organic compounds. Now this is just considering carbon and hydrogen. What happens when we add oxygen and nitrogen and sulfur? I mean, it's immense. It's almost infinite. It's staggering. This is a really big branch of chemistry. On the next page, I'm going to ask you to learn the names and formulas of the first 100 N-alkanes. This may sound arduous, but you'll see it follows very simple patterns, and there's practical use for it. Later on in 5th semester, you'll be talking about fats, oils, and waxes that have 46 carbons on one side and 62 on the other, and how are you going to name that unless you can name up to 100 carbons in an alkane. On page 48 and 49, we have the names of the first 100 alkanes. These are the Iupac names, and I trust you're familiar with the first 10 already. I'll go through these relatively quickly, and you can spend as much time as you need to. Methane, ethane, propane, and butane. And after that, the prefixes are pretty common. Pentane, hexane for 6, heptane for 7, octane for 8, nonane for 9. We get to 10, that would be decane, the decimal system based on 10. Now what would 11 be? Well, it's going to be called 1 plus 10, and the prefix for that is un, so it's going to be undecane, or 1 plus 10. 12 is 2 plus 10, which would be dodecane, tridecane for 3 plus 10, and the rest get easy now. Tetradecane, pentadecane, hexadecane, heptadecane, octadecane, and nonadecane. Now from 20 to 29 is the most difficult part between 1 and 100. They are different than the rest. Let's plow through these and then you'll see how easy the rest are. So 20 is called icosane. If you're an arithmetic person, you may be familiar with the term icosahedron. An icosahedron is a 20-sided structure. Now how do you say 21? You're probably going to think un, but it isn't. It's hen. So it's henicosane. So from here on in, 1 will be hen rather than un. And 22 is docosane. 23 is tricosane, and so on down to the end, as you might predict at this point. Tetracosane is 24, pentacosane 25, hexacosane 26, heptacosane 27, octacosane 28, and nonacosane 29. Again, the 20s are different. It makes it difficult to learn, but 30 to 100 is much easier. So look at 30. 30 is triacontane. 40 is tetracontane. 50 is pentacontane. And I'll bet you know what 60 is. It'd be hexacontane, heptacontane for 70, octacontane for 80, nonacontane for 90, and we'll get to 100. So these follow a very similar pattern and are easier to learn. So how do we say 31? It'd be hen triacontane. So we use hen for 1, and then it'd be do-triacontane for 2 plus 30, triacontane for 3 plus 30, tetra-triacontane for 4 plus 30, and so on down to the end. So we have pentatriacontane, hexatriacontane, heptatriacontane, octatriacontane, and nonatriacontane. So 30 is triacontane, 40 is tetracontane, 41 follows the same pattern as the 30s. It'll be hen tetracontane. And so on down the list. We have do-tetracontane, tri-tetracontane, tetra-tetracontane for 4 plus 40, penta-tetracontane is 5 plus 40, hexa-tetracontane 6 plus 40, hepta-tetracontane for 47, octa-tetracontane for 48, and nonatetracontane for 49. So 50 is pentacontane, so what's 51? It'll be hen pentacontane, 2 plus 50 is dopentacontane. 3 plus 50 is tripentacontane. 54 is tetrapentacontane. 55 is pentapentacontane. 56 is hexapentacontane, heptapentacontane, octapentacontane, nonapentacontane. And that brings us to 60. What would 60 be? That'll be hexacontane. Hen-hexacontane, 61. Do-hexacontane, 62. Trihexacontane, 63. Tetrahexacontane, 64. And I think you can get the rest of those. Look at 70s. For the 70s we have heptacontane. 71 will be hen-heptacontane. 72 is do-heptacontane, and so on down the list to nonaheptacontane. For the 80 group, we have octacontane, hen-octacontane, do-octacontane, and so on down to nona-octacontane. For carbon 90 to 99, we have nonacontane is 90, hen-nonacontane is 91, do-nonacontane is 92, and so on down to nona-nonacontane for 99. And finally, we have hectane for 100 carbons. So next time you sing 100 bottles of beer on the wall, you can start off using the names of the alkanes. You get hectane bottles of beer on the wall, hectane bottles of beer. If one of the bottles should happen to fall, there'd be nona-nonacontane bottles of beer on the wall, and so on down the list. Enjoy. On page 50, I have a summary of the nomenclature of the first 100 N-alkanes. At the bottom of the page, I have a short exercise. Let's try these. What's the name of an N-alkane with 38 carbons? Well, that'd be 8 plus 30. So that'd be called octa. And how do you say 30? Triacontane. How about an N-alkane with 75 carbons? That'd be 5 plus 70. That's penta, hepta, contane. All right, hexacosane. What's the formula for hexacosane? Well, that would be 6 plus 20, right? So that would be C, 26, H, 2N plus 2. That's 26 times 2 is 52, and 2 is 54. How about nona-tetracontane? Well, that's 9 plus 40 is 49, C, 49, H, 2N plus 2 sounds like 100. Okay, try this. How would you write the name and the formula for an 84 carbon N-alkane? Well, the formula would be C, 84, H, 168 plus 2 looks like 170. And the name would be 4 plus 80, which would be tetra, octa, contane. Piece of cake, right? On page 51, we're going to learn the common names of the alkyl groups. Now, an alkyl group is an alkane with one hydrogen either missing or replaced by something else. So an alkyl group would be C to the N, H2N plus 1. The simplest alkyl group would be the methyl group, CH3 something. So here it is, the methyl group, simplest of alkyl groups. When we get to ethyl group, there are 6 hydrogens that can be removed or replaced, and they're all equivalent. It doesn't matter which one is removed. The ethyl group is CH3, CH2, something. When we get to propane, there are actually 2 different kinds of hydrogens. There are 6 hydrogens on the methyl groups that are equivalent, but they're different than the 2 hydrogens on the methylene group. So if you remove any one of the 6 hydrogens on the methyl group, we get what's called an N-propyl group. That'd be CH3, CH2, CH2 something. Abbreviated C3H7. That's N-propyl. On the other hand, if a hydrogen is removed from the central carbon, from the methylene group, the isopropyl group is what's formed, CH3, CH something, CH3. Now they're different. Take a look at the animations here. So this is N-propyl chloride. We replaced the hydrogen from one of the N carbons with a chlorine, and the C3H7 group is called an N-propyl group. Now this is called isopropyl. The hydrogen on the central carbon has been removed or replaced, in this case replaced with a chloride, and so this is called isopropyl chloride. So the term iso, we've had that before, right? We learned that an isoalkane has a methyl group on a carbon second to either end of the chain. It didn't matter which. Well, when we talk about alkyl groups, it does matter. Isoalkyl means that there's a methyl group on the second last carbon in the chain. That's the second last carbon from the head carbon being the beginning of the chain. So look at isopropyl. The central hydrogen has been removed. That by definition becomes the head carbon. This is the first carbon in the chain. And so the last carbon would be either the one on the left or the one on the right. Let's go left. This is the last carbon, and the second last carbon from the end comes right back to the first again. This is an odd case where the second last happens to be the same as the first, but it is the case, and that's called isoalkyl. Now you say that doesn't even look like an iso. I thought iso meant there was a methyl group second to the end. I don't see the methyl group. But look at the structure here. If I just turn the bonds around, here's the methyl group situated on the second last carbon from the end of the chain. So again, please note the head carbon is by definition the first carbon in an alkyl group, and everything's determined from that. Now you need to learn, and I will teach you, the isoalkyl group names for up to 6 carbons. Take a look at the next page. So continuing on page 52, we're looking at the nomenclature of the alkyl groups. And I've learned that this can be pretty daunting for students. I recall one time I taught this class, and one of the better students got up and left the class in the middle and left the program and never came back. So even though I got this from a textbook and it seemed logical to me, it wasn't easy to follow. So I have found a much easier way to present this, and I'll show you in just a moment, so don't panic by this. But there is something here that's simple, and we do need to continue. This carbon at the end of the chain is bonded to one other carbon, and therefore it's called a primary carbon. A primary carbon is bonded to one other carbon. We need this nomenclature, as you'll see. Now a primary carbon can have up to 3 hydrogens bonded to it, and a hydrogen that's bonded to a primary carbon is called a primary hydrogen. This carbon here is bonded to 2 other carbons, and so it's called a secondary carbon. A secondary carbon is bonded to 2 other carbons. And a secondary carbon can have up to 2 more hydrogens bonded to it, and if there's a hydrogen bonded to the secondary carbon, it would be called a secondary hydrogen. This carbon here in the middle is bonded to 3 other carbons, and therefore it's called a tertiary carbon. Note that a tertiary carbon can have up to 1 more hydrogen bonded to it, and such a hydrogen would be called a tertiary hydrogen. Now this is a quaternary carbon. It's bonded to 4 other carbons, and a quaternary carbon has no more bonds available, so you cannot have a quaternary hydrogen. That wasn't bad, right? One more thing here. Sometimes in organic structures and nomenclatures, we're focusing on one part of the molecule, and we just don't want to draw out all the rest of the molecules. Sometimes they're pretty big. So we use sometimes the symbol R, which stands for the rest of the molecule. And it's usually some kind of alkyl group. So if you see this structure, we would describe this carbon as being a primary carbon because it's bonded to some other alkyl group, R. This is a secondary carbon because it's bonded to other alkyl groups. This is a tertiary carbon that's bonded to 3 other alkyl groups, and this is a quaternary carbon because it's bonded to 4 other carbon groups. Occasionally, we'll be even more specific, and we might use the symbol AR, implying that it's not just any alkyl group, it's an aromatic group or aryl group. We'll get to that later. On page 54, I have an exercise that will make it very easy for you to learn the names of the common alkyl groups. And we'll start at the bottom. It's easiest to see if we start with the largest carbon group. And the common alkyl group names only apply up to 6 carbons, so you can take consolation in that. There's just not that many. So let's draw the structure of the alkyl chlorides of these descriptions. Let's start with N-hexyl chloride. So N-hexyl would have 6 carbons in an unbranched chain. There's 2, 3, 4, 5, 6. 2, 4, 6, and then a chloride attached to it. The head carbon is here, and that's the head of the chain. The end of the chain is at the other end, the left side. We learned that there's something called an iso group, and we can apply it to isohexyl. So there'll be 5 carbons in the main chain, 2, 3, 4, 5, and then the chloride. And the iso means there's a methyl group on the carbon second from the end of the chain. So again, the head carbon is the start of the chain. The opposite end is the end of the chain. Second from the end is the methyl group. That's called isohexyl chloride. It's easy to see it here. Now we have neohexyl chloride. So that'll have 4 carbons in the main chain, 2, 3, 4, and then the chloride. And we learned that neo means that there's 2 methyl groups on the carbon second from the end of the chain. Again, the head carbon is here, and the end of the chain is the left side, second from the end, 2 methyl groups. That is neohexyl chloride. Easy to spot. Let's do the 5 carbon alkyl chlorides. We'll start with N-pentyl chloride. That'd be 5 carbons in the main chain, 2, 3, 4, 5, and then the chloride. That'll be N-pentyl chloride. How about isopentyl? Well, that would have a methyl group second from the end, so there'll only be 4 carbons in the main chain. That's 2, 3, 4, and then the chloride. We have a methyl group second from the end of the chain. Again, the head carbon is the carbon that's in which the hydrogen has been replaced, and so the end of the chain is the left side, second from the end is the methyl group. We also know how to draw a neopentyl. We'll have 3 carbons in the main chain. There's 2 and 1 is 3, and then the chloride. Then we have 2 methyl groups second from the end of the chain. That'll be neopentyl chloride. There's one additional common name alkyl group for pentyls, and it's tert. So tert pentyl looks like this. We've got 4 carbons in the main chain, a methyl group, and the chloride is situated here. So my head carbon is here. This is called tert, sometimes written as T, short for tertiary, sometimes written this way, tertiary. What this means is that the head carbon is a tertiary carbon. It's bonded to 3 other carbons, and that has a lot of importance in terms of its reactivity, and somebody named it and it's stuck. So that is called tert pentyl alkyl group, in this case tert pentyl chloride. So those are 4 common alkyl group names that we can apply to the pentyls. Let's go with the 4 carbon groups, the butyls. N-butyl chloride would have 4 carbons in the main chain, 2, 4, and then the chloride. Isobutyl will have 3 carbons in the main chain, 2 and 1 is 3, and then the chloride. And then we have a methyl group second from the end of the chain. Again, here's the head, here's the end of the chain. That's, I'll put E here. Second from the end is the methyl group. Tert butyl. Tert butyl has a tertiary carbon. It looks like this. So there's 1, 2, 3, 4, and here's the chloride. So our head carbon is right here, and so it's a tertiary carbon because it has 3 carbons attached to it. It's an odd name, eh? You might think, well, that should have been called neo-butyl. I wouldn't argue that because it has the neo structure. Here's the head carbon, here's the end. Second from the end is 2 methyl groups, so it could have been named neo-butyl, but it's called tert-butyl, T-butyl, because it's a tertiary carbon that has a lot of significance in its reactivity, as you'll see later. There's one last group I haven't shown you yet. It's called a sec-butyl group. 4 carbons in the main chain, and the chlorine is on a secondary carbon. This carbon, the head carbon, is bonded to 2 other carbons, so it's called secondary, or sec. Often we just write S-butyl, sec-butyl. Sec only applies to 4 carbon groups. There's no sec-pentyl or any other application. And finally we have the propyl groups. We have N-propyl. There's 3 carbons, and then chloride, that would be N-propyl. Isopropyl, we've had this before. It looks like this. Here's the head carbon. Here's the end carbon. Propyl. Second from the end is a methyl group. That's isopropyl chloride. So the good news is that's all there are. There are no other common alkyl names. With practice, it's not so bad. Page 61. Let's get some practice with the common alkyl group names. It's easiest, believe it or not, to start with the largest alkyl groups. They're easier to see. We're just going to fill out the left-hand column for the common system. We'll do the right-hand column using a Iupac later. See, here we have the head carbon, and there's 6 carbons in the chain, so it's unbranched, and that would then just be N-hexyl, or you could just say hexyl, cyclohexane. Beneath that, the head carbon is here. We have 5 carbons in the main chain and a methyl group on the second carbon from the end of the chain. So the head carbon is the beginning of the chain, so this is second from the end. A methyl group second from the end of the chain is called iso. There's still 6 carbons in all, so it will be hexyl. It's iso, hexyl, cyclohexane. When you use the prefix iso, it is not hyphenated. Look at the next example. Head carbon, 1, 2, 3, 4, 5, 6 carbons. There's 2 methyl groups, second from the end of the chain. That looks like neo-hexyl, cyclohexane. Neo means there are 2 methyl groups, second from the end of the chain. Neo is not hyphenated. Let's look at the Pentyl Cyclohexane group. So here again is the head carbon, carbon 1, and there are 5 carbons in this chain, so it's going to be pentyl. It is unbranched, so it's simply going to be N, or you can leave that out and just say pentyl cyclohexane. The one below it, the head carbon, is here. There are 4 carbons in the main chain and 1 methyl group. 5 in total. It's going to be some type of pentyl. Which one? Well, it's going to be isopentyl, because there's a methyl group on the carbon second from the end of the chain. Next one, head carbon's here. 1, 2, 3, 4, 5. Again, it's a pentyl group. Which one? Well, the carbon second from the end of the chain has 2 methyl groups on it. Do you recall? That is called neo-pentyl cyclohexane. And the last one here, the head carbon is bonded to 3 other carbons. Don't look at the cyclohexane ring, but aside from that, there is 3 carbons attached to the head carbon in the alkyl group, and therefore that one is called tert, or T, pentyl cyclohexane. Let's look at the butyls. Butyl cyclohexane. The first example here, the head carbon is here, and it's an unbranched chain. So that would be simply N, or simply butyl cyclohexane. Next example, head carbon is here. 3 carbons in the main chain and a branch, a methyl group second from the end. Sounds to me like isobutyl cyclohexane. Alright, the next one, the head carbon is here, and there are 3 carbons attached to it. It's a 4-carbon group, so it's some type of butyl. This one is called tert, or T-butyl cyclohexane. The last one here, the head carbon is here. There's 4 carbons in total in the branch, therefore it's some type of butyl. Notice the head carbon is bonded to 2 other alkyl groups in the alkyl group itself. Don't look at the cyclohexane. That could have been a chloride or something else. So that's called sec, or S-butyl cyclohexane, because the head carbon is secondary. Alright, the propyl cyclohexanes, there's only 2 of them. We'd have N-propyl, or I could just say propyl cyclohexane. The other one, head carbon is here, and you see it's branched. It has to be isopropyl. Recall that there's a methyl group attached to the second last carbon in the chain. It's iso. So in fact, this is isopropyl cyclohexane. Then we have ethyl cyclohexane, and methyl cyclohexane. And that's it. Those are all of the common alkyl group names. They only apply systematically up to a maximum of 6 carbons.